There is a moon orbiting Saturn right now that should be dead. It is smaller than the state of Arizona. It orbits nearly 1 billion miles from the Sun. It receives so little heat that its surface temperature drops to negative 223 degrees Celsius. By every rule of planetary science, this world should have frozen solid billions of years ago and stayed that way forever. But in 2005, a spacecraft flew past it and saw something that should have been impossible. Columns of water were erupting from cracks in its south pole, blasting ocean material into space at over 800 miles per hour. The moon was not dead. It was expelling the contents of a hidden sea. And everything scientists thought they knew about small icy worlds collapsed overnight. If you enjoy journeys that shatter assumptions about what the universe is hiding in plain sight, hit that like button and subscribe. Also, we're now live on Spotify. The link's in the description if you'd like to listen to us wherever you are. Now, with that all said and done, let's begin. Look at a list of Saturn's moons, and you will find Enceladus buried somewhere in the middle. Not the biggest, not the most colourful, not the most famous, just another name on a roster of over 140 frozen satellites circling a gas giant nearly 1 billion miles from the Sun. On paper, Enceladus is one of the least interesting objects you could study. It measures roughly 500 kilometers across, which makes it small enough to fit comfortably inside the borders of Arizona. Its surface is covered in water ice so pure and so reflective that it bounces back nearly all the sunlight that reaches it. The temperature on that surface drops to approximately negative 223 degrees Celsius in the coldest regions. There is no atmosphere worth mentioning, no obvious geological drama, no volcanic plumes visible from afar. For most of the history of modern astronomy, Enceladus was exactly what it appeared to be. A tiny ball of ice drifting through the outer solar system in total silence. And that assessment made perfect sense. Planetary scientists have known for decades that a body's ability to remain geologically active depends overwhelmingly on its size. Larger worlds retain internal heat longer because their volume-to-surface area ratio slows the rate at which energy radiates into space. Earth, at nearly 13,000 kilometers across, still has a molten mantle, driving plate tectonics, volcanic eruptions, and earthquakes, 4.5 billion years after formation. Mars, roughly half Earth's diameter, went geologically quiet billions of years ago. Its core is cooled, its volcanoes stopped. Its magnetic field collapsed. The pattern is consistent and well understood. Small bodies cool fast. They lose their internal heat within a few 100 million years, sometimes less. Once that heat is gone, geological activity ceases. The world becomes inert. It becomes a relic. It becomes dead. Enceladus is roughly 13 times smaller than Mars. By every reasonable calculation, it should have frozen solid before the first complex life appeared on Earth. Its rocky core should have cooled into a rigid, immovable mass early in solar system history. Whatever primordial warmth it carried from its formation should have radiated away into the vacuum of space long ago. There should be nothing happening inside this moon, nothing flowing, nothing churning, nothing alive in any geological sense. Enceladus should be a corpse. This expectation was so deeply embedded in planetary science that nobody seriously questioned it for over 200 years. The moon was discovered in 1789 by William Herschel using a homemade 40-foot reflecting telescope in the English countryside. He noted its existence, recorded its orbit, and moved on. The name itself came from Greek mythology. Enceladus was one of the giants, a titan buried alive beneath the earth by the goddess Athena after his defeat in a primordial war. The ancients believed his restless body caused earthquakes and volcanic eruptions from below the ground. It is an almost eerie coincidence. A moon named after something imprisoned and raging beneath a surface turned out to contain exactly that. For nearly 2 centuries after that, Enceladus remained a faint dot in the eyepieces of the world's best telescopes. Too small, too far, too cold to warrant sustained attention. It existed in the scientific record as a footnote, a frozen object catalogued and essentially forgotten. Then something strange happened. In 1980 and 1981, the Voyager 1 and Voyager 2 spacecraft flew through the Saturn system on their grand tour of the outer planets. Voyager 1 passed Saturn in November 1980, providing the first close-range images of several Saturnian moons. Voyager 2 followed in August 1981 and returned the first moderately detailed photographs of Enceladus. The images were grainy by modern standards, but they contained something that did not fit. Parts of the surface looked wrong. Several regions appeared unusually smooth with almost no impact craters visible. In a solar system where every small body had been battered by billions of years of meteorite bombardment, a smooth surface was a red flag. Impact craters accumulate over time. The fewer craters you see, the younger the surface must be. Some terrain on Enceladus appeared to be geologically young, perhaps only a few 100 million years old, maybe younger. That should have been impossible for a frozen moon this small. Scientists noticed. They published papers speculating about possible resurfacing mechanisms, but the Voyager data was limited. Resolution was low, coverage was incomplete. Without more information, the anomaly remained a curiosity rather than a crisis. Enceladus went back to being a minor moon with a peculiar surface. Interesting but not urgent. It would take another 2 decades and a far more capable spacecraft before the truth detonated across planetary science. The Cassini spacecraft arrived at Saturn on June 30, 2004, after a nearly 7-year journey from Earth. Built jointly by NASA, ESA, and the Italian Space Agency, Cassini was the most sophisticated robotic explorer ever sent to the outer solar system. It carried 12 scientific instruments designed to study Saturn, its rings, and its moons in extraordinary detail. Its companion probe, Huygens, descended to the surface of Titan in January 2005 and returned the first images from the surface of a moon in the outer solar system. Cassini itself would remain in orbit around Saturn for the next 13 years, conducting 127 close flybys of Titan, 23 targeted flybys of Enceladus, and countless observations of the ringed planet and its other satellites. Nobody expected Enceladus to be the mission's most important discovery. Titan was the star attraction, a world larger than Mercury with a thick nitrogen atmosphere, methane lakes, and complex organic chemistry. Enceladus was on the observation schedule, but it was not the priority. It was too small, too simple, too dead. The first close flyby in February 2005 was planned primarily to improve orbital models and test instruments. It was almost routine. Almost. On that first pass, the spacecraft's magnetometer detected something that immediately raised alarms among the science team. The magnetic field around Enceladus was being distorted in ways that suggested the moon was interacting with Saturn's magnetosphere far more strongly than a small inert ice ball should. Something was generating a cloud of charged particles around the moon. Something was actively producing material and releasing it into space. The July 2005 flyby changed everything. Cassini dove to within 173 kilometers of the surface, and its instruments recorded data that would ultimately rewrite textbooks. The composite infrared spectrometer detected anomalously high temperatures along 4 roughly parallel fractures near the South Pole. These fractures, each approximately 130 kilometers long and spaced about 35 kilometers apart, were radiating heat far above the background temperature of the surrounding terrain. Scientists would later name them tiger stripes, a casual label for features that turned out to be among the most scientifically explosive discoveries in the history of planetary exploration. The temperatures along the tiger stripes reached as high as -93 degrees Celsius in some localized spots. That might sound brutally cold by human standards, but on a world where the average surface temperature hovers near -200 degrees, a reading of -93 is volcanic. It means something beneath those fractures is generating heat and pushing it toward the surface. Something active, something ongoing. But the temperatures were only the beginning. Cassini's cameras and spectrometers revealed that the tiger stripes were not merely warm. They were erupting. Towering columns of fine ice particles and water vapor were shooting upward from the fractures into space, forming a vast plume visible against the blackness when backlit by the sun. The plume extended hundreds of kilometers above the South Pole, a feathery spray of material escaping the moon's weak gravity and streaming outward into Saturn's orbital environment. This was not a subtle observation requiring careful statistical analysis. This was an eruption visible in photographs. Enceladus was actively venting material into space. right now, in real time. The implications were immediate and enormous. A frozen moon 500 kilometers wide, orbiting nearly 10 astronomical units from the Sun, was behaving like an active world. It was not merely warm in places. It was expelling material from its interior through discrete fractures, powered by an internal energy source that should not exist according to everything scientists understood about how small icy bodies age. The word that kept appearing in mission reports and press conferences was impossible. Not technically impossible, because the evidence was undeniable, but impossible in the sense that the existing mental model of what a moon like this should be could not accommodate what Cassini was seeing. Over the following months and years, Cassini returned for closer and more targeted flybys. Each pass brought new instruments to bear, and each set of results deepened the shock. The ion and neutral mass spectrometer sampled the plume directly during several flybys and identified its composition with increasing precision. The plume contained water vapor as its primary component, which was expected if ice was sublimating or liquid water was boiling into the vacuum. But mixed into that water vapor was a cocktail of molecules that told a far more complex story. Carbon dioxide, methane, ammonia, molecular hydrogen, simple organic compounds, and salts, sodium chloride and potassium chloride, the same salts that make Earth's oceans salty, were embedded in the ice grains being ejected from the fractures. The salt detection was a turning point. You do not get sodium and potassium salts from sublimating surface ice. You get them from liquid water that has been in prolonged contact with rock. The chemical signature was unmistakable. Somewhere beneath the frozen surface of Enceladus, liquid salt water existed, not as a theoretical possibility, not as a vague inference. The salt was there, embedded in ice grains that Cassini's cosmic dust analyzer caught and measured, as the spacecraft flew through the plume at speeds exceeding 7 kilometers per second. Enceladus had an ocean. More than 100 individual geysers were eventually identified along the tiger stripe fractures. Each geyser marked a point where subsurface material was reaching the surface and escaping into space. The total mass ejection rate was estimated at roughly 200 kilograms per second. Every second, 200 kilograms of water vapor, ice crystals, salts, and organic molecules were being launched off this tiny moon and hurled into space. Some of that material fell back to the surface as fresh snow, gradually building up deposits hundreds of meters thick around the South Polar region. The rest escaped Enceladus entirely and entered orbit around Saturn, where it spread out to form and continuously replenish Saturn's E-ring, a faint but vast ring of ice particles encircling the planet. This single discovery answered a question that had puzzled astronomers for decades. Saturn's E-ring was unusually broad and diffuse compared to the planet's other rings. Ring particles are constantly being eroded by micrometeorite impacts and dispersed by gravitational perturbations. Without a continuous source of fresh material, the E-ring should have dissipated long ago. Enceladus was that source. A tiny moon was single-handedly maintaining one of Saturn's largest ring structures through its ongoing volcanic activity. The ring itself was evidence that the eruptions were not a recent or temporary phenomenon. They had been occurring long enough to build and sustain a planetary-scale feature. The eruptions also explained why Enceladus has the highest albedo of any body in the solar system. Albedo measures how much light a surface reflects. Fresh snow on Earth reflects about 80 to 90% of incoming sunlight. Enceladus reflects over 80% of incoming sunlight, making it the most reflective body in the solar system by a wide margin. Its surface is coated in a continuous rain of ultrafine ice particles falling back from its own plumes, creating a pristine white shell that makes the moon the most reflective object orbiting any planet. Even this basic observational fact, the moon's extraordinary brightness, turned out to be a consequence of its internal activity. Nothing about Enceladus was passive. Nothing about it was dead. But determining the nature and extent of the ocean required more than plume chemistry. The critical breakthrough came from gravity science. During close flybys, Cassini's radio signal was tracked from Earth with extreme precision. As the spacecraft passed near Enceladus, the moon's gravity tugged on it, causing tiny shifts in the radio signal's frequency. By measuring these frequency shifts, scientists could map the distribution of mass inside the moon. The results published in 2014 revealed a gravitational anomaly beneath the South Polar region, consistent with a body of liquid water roughly 10 kilometers deep. The ocean was real. The ocean was there, and it was being sustained by processes that a moon this size should have exhausted billions of years ago. But the gravity data told only part of the story. Researchers studying Cassini's imaging data noticed something subtle about how Enceladus rotated. The moon's spin was not perfectly locked to its orbit in the way a rigid body would be. Instead, Enceladus exhibited a slight physical libration, a wobble in its rotation that was larger than it should have been if the ice shell were frozen solid all the way down to the rocky core. The only way to produce a libration that large was if the outer ice shell was mechanically decoupled from the interior. If a layer of liquid separated the ice from the rock, this meant the ocean was not confined to the South Pole. It was global. Enceladus possessed a world-encircling ocean beneath its ice, wrapping the entire moon in a shell of liquid saltwater hidden from view, but announced to the universe through the plumes erupting from its south pole. The libration measurement itself was a triumph of patient, meticulous analysis. Researchers led by Peter Thomas at Cornell University spent years studying hundreds of Cassini images taken during different flybys, each captured from a slightly different orbital geometry. By tracking the precise positions of surface features, craters and ridges whose coordinates were known to high accuracy, the team could measure how much the surface shifted between images in ways that could not be explained by the spacecraft's own motion or the moon's orbital geometry. The residual shift was the libration. Extracting it required accounting for every other source of apparent motion, correcting for camera pointing errors, adjusting for the changing distance and angle of each flyby, and building a statistical framework robust enough to distinguish a real physical wobble from accumulated measurement noise. The final result, published in 2015, showed a libration amplitude of approximately 0.12 degrees. It does not sound like much, but when the researchers plugged that number into structural models of Enceladus, the implications were stark. No plausible arrangement of solid ice connected to solid rock could produce a wobble that large. The ice shell had to be floating. The reaction within the planetary science community was a mixture of excitement and disbelief. Many researchers had favoured models where the ocean was regional, a South Polar Sea perhaps a few hundred kilometres across, large enough to feed the plumes but small enough to explain why activity was confined to one hemisphere. A global ocean demanded a complete rethinking of the moon's thermal structure. If liquid water extended from pole to pole, the heat source could not be localised. The tidal heating had to be operating throughout the moon's interior, maintaining liquid conditions everywhere, not just beneath the active South Pole. The mental model of Enceladus as a frozen moon with a warm patch gave way to a far more radical picture, a world-encircling sea whose existence had been hidden by the very ice shell floating on top of it. Consider what this means. A moon that nobody took seriously for over 2 centuries turned out to contain a global ocean of liquid water. A body so small that its entire surface area is comparable to the nation of Turkey was harbouring a hidden sea beneath a shell of ice. A world receiving roughly 1% of the sunlight that falls on Earth was keeping that water liquid through internal processes that defied the standard expectations of planetary science. Everything about Enceladus contradicts the assumption that small icy moons are dead. Everything about it demanded an explanation. The plumes themselves became windows into a world no camera could photograph. Every molecule detected in the spray provided a clue about conditions deep below. The ice grains were not uniform. Some were almost pure water ice. Others were rich in salts. Still others contained organic compounds with complex molecular structures. The variation suggested that different source regions within the ocean were contributing material to the plumes, each with slightly different chemistry. The ocean was not a homogeneous body of salt water. It had chemical gradients, regions of different composition, a structure that hinted at active processes mixing and circulating material through the liquid interior. The organic molecules were particularly striking. Cassini's cosmic dust analyzer detected organic-bearing ice grains with molecular masses exceeding 200 atomic mass units. These were not simple molecules like methane or ethane. These were large, complex compounds with structures suggesting they had formed through sustained chemical processing in a liquid environment. Their presence in the plume meant that the ocean of Enceladus was not just salty water sitting passively beneath ice. It was a chemically active environment, producing complex organic material through reactions that required energy, time, and the right conditions. The kind of conditions found on Earth at hydrothermal vents on the deep ocean floor. By the time Cassini ended its mission in September 2017, plunging deliberately into Saturn's atmosphere to avoid contaminating any of the planet's potentially habitable moons, the spacecraft had transformed Enceladus from a footnote into one of the most important objects in the solar system. A moon that had been ignored for over 200 years was now recognized as an active ocean world with confirmed liquid water, confirmed salts, confirmed organic chemistry, and confirmed energy output that could not be explained by any passive process. But recognizing that Enceladus is active only sharpened the central mystery. This moon is tiny. It orbits at a distance from the Sun where temperatures are crushing. It has no right to possess liquid water, let alone vent it into space in 100-kilometer-tall columns of vapor and ice. The question that Cassini answered, whether Enceladus is geologically alive, immediately gave way to a deeper question that the spacecraft could only begin to address. What is keeping this moon alive? What engine is running beneath that ice, generating enough heat to maintain a global ocean and power a continuous field of geysers on a world that every model said should have gone cold and silent before the dinosaurs existed on Earth? The answer lies not above the ice, but far below it, in a gravitational relationship with Saturn so powerful that it has been warping and flexing the interior of this moon for billions of years without stopping. Every world in the solar system was born hot. When the planets and moons coalesced from the disk of gas and dust surrounding the young sun approximately 4.5 billion years ago, the process of accretion itself generated enormous heat. Material slamming together at high velocity converts kinetic energy into thermal energy. The larger the body, the more violent the collisions, the more heat gets trapped inside. Earth accumulated so much accretional energy that its entire interior melted, allowing heavy elements like iron and nickel to sink toward the center and form a dense metallic core, while lighter silicates floated upward to create the mantle and crust. 4.5 billion years later, Earth's interior remains molten. Heat still drives convection currents in the mantle. Tectonic plates still grind against each other. Volcanoes still erupt. Our planet is still geologically alive because it was born large enough to hold onto its primordial heat across the full span of solar system history. But size is everything in this equation. A body half Earth's diameter has roughly 1/8 the volume, but only 1/4 the surface area. The ratio between internal heat storage and surface heat loss shifts dramatically. Smaller worlds radiate their energy into space faster than large ones. Mars, at about half Earth's width, went geologically quiet roughly 3 billion years ago. Its volcanoes stopped. Its magnetic dynamo shut down. Its interior cooled below the threshold needed to drive any kind of active surface geology. The Moon, even smaller, lost its internal heat even faster. It has been tectonically dead for over 1 billion years. Enceladus measures slightly smaller than the straight-line distance between Los Angeles and San Francisco. In the hierarchy of solar system bodies ranked by ability to retain internal heat, Enceladus sits so far down the list that it barely registers. Its rocky core, estimated at roughly 350 to 400 kilometers across, should have radiated away every joule of primordial heat within the first billion years of its existence. Radioactive decay of elements like uranium, thorium, and potassium in that rocky core can generate some additional warmth over time. But for a body this small, the production rate is pathetically low compared to the rate at which heat escapes through the surface. Run the numbers using standard thermal models, and Enceladus should have frozen solid before complex life appeared on Earth. Its interior should be cold, rigid, finished. Yet Cassini measured a combined heat output from this moon of roughly 54 gigawatts. To put that in perspective, 54 gigawatts is equivalent to the total electrical generating capacity of a medium-sized industrialized nation. It is enough power to run approximately 54 nuclear reactors simultaneously. And this energy is not stored heat slowly leaking out from ancient times. This is heat being actively generated right now, in real time, inside a moon that has no business producing it. Radioactive decay in the core can account for perhaps 300 megawatts at most. The remaining 53 plus gigawatts have to come from somewhere else entirely. The source is Saturn itself. Or more precisely, the source is the gravitational relationship between Enceladus, Saturn, and a neighboring moon called Dione. Understanding how this relationship generates enough heat to sustain a global ocean inside a tiny ice world requires stepping back and examining one of the most powerful geological engines in the solar system. An engine that runs on gravity and geometry rather than chemical fuel or nuclear reactions. Enceladus does not orbit Saturn in a perfect circle. Its orbit is slightly elliptical, meaning the distance between the Moon and the planet varies throughout each orbital period of approximately 33 hours. At its closest approach, Enceladus swings roughly 236,900 kilometers from Saturn's center. At its most distant point, it moves to roughly 239,200 kilometers. The difference is small in percentage terms, but the gravitational consequences are enormous. Saturn is a gas giant with a mass 95 times that of Earth. Its gravitational field is immense, and gravitational force follows an inverse square relationship with distance. Even a slight change in distance produces a measurable change in the gravitational pull experienced by Enceladus. As Enceladus moves along its elliptical orbit, the strength and direction of Saturn's gravitational tug shift continuously. When the Moon is closer to Saturn, the tidal force is stronger. The near side of Enceladus gets pulled harder than the far side, creating a stretching effect along the line connecting the Moon to the planet. When Enceladus swings farther away, the tidal force weakens and the distortion partially relaxes. This cycle repeats every single orbit. Every 33 hours, Enceladus is squeezed and squeezed again by Saturn's tidal grip. The effect is analogous to repeatedly kneading a ball of bread dough. Every compression and extension cycle deposits a small amount of energy into the material as friction. The dough gets warmer. Do it fast enough and long enough, and the heat accumulates. Enceladus has been experiencing this gravitational kneading for billions of years. Every orbit generates friction inside the Moon. Every cycle converts a tiny fraction of orbital energy into thermal energy. Accumulated over geological time, the effect is staggering. The scale of this deformation is not dramatic by human standards. Enceladus does not visibly stretch and compress like a rubber ball being squeezed. The tidal distortion across the entire body amounts to perhaps a few meters of displacement, a bulge so subtle that standing on the surface you would never perceive it. But a few meters of displacement distributed across the entire spherical volume of the Moon's rock, ice, and liquid water represents an enormous amount of mechanical work. Every cubic meter of the interior participates in the flexing. Every grain boundary in the rocky core, every crystal lattice in the ice shell, every current in the intervening ocean absorbs a fraction of the tidal energy and converts it into heat through internal friction. The process is not concentrated at a single point. It is distributed throughout the entire volume of the Moon, with different layers and materials responding to the flexing at different rates and contributing different amounts of heating. The ice shell and the ocean are particularly effective at dissipating tidal energy. Ice is a viscoelastic material, meaning it behaves partly like a solid and partly like a viscous fluid, depending on how quickly the stress is applied. Over the 33-hour orbital period, the ice shell flexes enough to generate measurable internal friction without cracking catastrophically across most of its surface. The exception is the South Polar region, where the ice is thinnest and the tidal stresses are most concentrated. There, the flexing does produce fractures, the tiger stripes, and those fractures become conduits for ocean material to reach the surface. The ocean itself also dissipates tidal energy through viscous friction as the water sloshes back and forth in response to the changing gravitational pull. This oceanic tidal dissipation may contribute a significant fraction of the total heat budget, though the exact proportion remains debated among researchers. The rocky core contributes as well, but its role is more complex. If the core is rigid and monolithic, it dissipates relatively little tidal energy, because solid rock at these temperatures does not flex easily. But some models suggest the core may be unconsolidated, a porous rubble pile of rocky fragments with water percolating through the gaps. A porous, water-saturated core would dissipate tidal energy far more efficiently than a solid one, because the water flowing through narrow channels between rock fragments generates friction at every contact point. This scenario would also explain the strong evidence for hydrothermal activity, as heated water circulating through a porous core would interact with rock surfaces across an enormous total area, driving the chemical reactions whose products Cassini detected in the plume. Whether the core is solid or porous remains one of the most important unresolved questions about Enceladus's internal structure, and the answer significantly affects estimates of how much tidal heat the Moon generates and where that heat is concentrated. But there is a problem with this picture. If Enceladus were orbiting Saturn alone, tidal forces would gradually circularize its orbit. As the orbit becomes more circular, the variation in tidal stress decreases. Less variation means less flexing. Less flexing means less heat. Eventually, the orbit would become perfectly circular. The tidal heating would stop and the Moon would freeze. This is what should have happened. Enceladus should have lost its orbital eccentricity long ago and gone cold. The reason it did not is Dione. This neighbouring moon, roughly 1,100 kilometres in diameter, orbits Saturn at a greater distance than Enceladus. The two moons are locked in what physicists call a 2-to-1 orbital resonance. For every single orbit Dione completes around Saturn, Enceladus completes exactly 2. This is not a coincidence. It is a gravitational lock. Every time the two moons reach the same relative position, Dione gives Enceladus a small gravitational tug that prevents its orbit from circularizing. The resonance continuously pumps eccentricity back into Enceladus's orbit, counteracting the circularizing effect of tidal friction. It is a self-sustaining loop. The eccentricity drives tidal heating. The tidal heating dissipates orbital energy. The resonance with Dione replaces that energy. The cycle continues indefinitely. This mechanism is not unique to Enceladus. The same process powers the most volcanically active body in the solar system, Jupiter's moon, Io. Io is locked in a complex orbital resonance with Europa and Ganymede. Jupiter's tidal forces flex Io so violently that the moon is covered in hundreds of active volcanoes, erupting sulfur and silicate lava across its tormented surface. The physics is identical. A large planet provides the tidal force. An orbital resonance with neighbouring moons maintains the eccentricity. The result is internal heating on a scale that defies the moon's size, but there is a critical difference between Io and Enceladus that makes the Saturnian moon situation far more scientifically extraordinary. Io is large, roughly 3,600 kilometers in diameter, and orbits extremely close to Jupiter, the most massive planet in the solar system. The tidal forces acting on Io are immense. It would almost be surprising if Io were not volcanically active. Enceladus, by contrast, is 7 times smaller in diameter. It orbits Saturn, which is 3 times less massive than Jupiter. It sits farther from its parent planet in relative terms. The tidal forces acting on Enceladus are dramatically weaker than those acting on Io. Yet Enceladus still manages to generate enough internal heat to maintain a global liquid ocean and power over 100 geysers. The efficiency of its internal heating mechanism is remarkably high for a body this small. Understanding exactly how the heat is distributed through the interior and how it reaches the surface remains an active area of research. The key evidence for the global nature of the ocean came from an elegant analysis of Enceladus's rotation. In 2015, researchers studying Cassini imaging data measured the moon's libration with unprecedented precision. Libration, in this context, refers to a slight back-and-forth wobble in the moon's rotation as it moves along its elliptical orbit. Every orbiting body locked in synchronous rotation with its planet experiences some degree of libration, but the amplitude of that wobble depends critically on the internal structure. If Enceladus were a solid body, frozen from surface to core with the ice shell rigidly attached to the rocky interior, the libration would be small. The entire moon would rock as a single rigid unit, and its large total mass would resist the wobble. What Cassini measured was a libration roughly 3 times larger than a solid body could produce. The only way to explain the observed wobble was if the ice shell was not connected to the rocky core at all. If a layer of liquid separated the two, the ice shell would be free to wobble independently, like the loose shell of an egg sloshing on a table. Because the shell alone has much less mass than the entire moon, it responds more dramatically to the tidal torque. The measured libration amplitude was consistent with a global ocean extending beneath the ice shell across the entire body of Enceladus. Not just a regional sea beneath the South Pole, but a continuous planetary ocean surrounding the rocky core. This was a profound result. Before the libration measurement, many scientists had assumed the ocean was a localized feature, perhaps a lake or sea confined to the South Polar region where the plumes erupted. A regional ocean could be explained by localized heating, perhaps a hotspot in the core, but a global ocean demanded a global heat source. It meant that tidal heating was not confined to one region of the interior. It was operating throughout the moon, maintaining liquid water from pole to pole, even in regions where no surface activity was visible. Enceladus was not a frozen moon with a warm patch. It was an ocean world with an ice roof. The thickness of that ice roof became the next critical question. Modelling based on Cassini's gravity data, shape measurements, and the libration analysis converged on a picture where the ice shell varies in thickness from roughly 5 kilometers at the South Pole to over 20 kilometers at the equator and slightly more at the North Pole. This variation makes physical sense. The South Pole is where tidal heating is most intense and where the plumes erupt, so the ice is thinnest there. The equatorial and northern regions experience less heating, allowing thicker ice to accumulate. The ocean beneath has an estimated average depth of roughly 25 to 30 kilometers, sitting atop a rocky core, approximately 350 to 400 kilometers in diameter. In total, Enceladus consists of a rocky center wrapped in a global saltwater ocean, wrapped in turn by a shell of ice of varying thickness. The entire structure is being continuously warmed from within by the gravitational engine described above. For years, scientists assumed the North Pole of Enceladus was geologically quiet. Unlike the South Pole with its tiger stripes and spectacular plumes, the North Polar region appeared ancient, heavily cratered, and thermally dead. This made intuitive sense within a framework where tidal heating was concentrated at one pole. The South Pole was the active end, the North Pole was the frozen end. The moon had a hot side and a cold side. That framework collapsed in November 2025. A research team from Oxford University, the Southwest Research Institute, and the Planetary Science Institute published results in the journal Science Advances that revealed something Cassini had been hiding in its data for over a decade. By painstakingly analysing infrared measurements taken by Cassini's Composite Infrared Spectrometer, or CIRS, during flybys in 2005 and 2015, the researchers detected excess heat at the North Pole of Enceladus. The surface temperatures in the North Polar region were approximately 7 Kelvin warmer than they should have been if the only heat source was sunlight. 7 degrees might sound trivial, but on a world this cold, where the baseline temperature hovers near negative 200 degrees Celsius, 7 extra degrees is an enormous anomaly. The only plausible explanation was heat leaking upward from the ocean through the ice shell. The same process that drives the southern plumes, conductive heat transfer from a warm ocean through a cold crust, was also operating at the opposite pole. Extracting that 7 Kelvin signal from the data was extraordinarily difficult. The Cassini CIRS instrument measured surface temperatures by detecting infrared radiation emitted by the ice. But those temperatures fluctuate constantly due to the day-night cycle. The changing distance from the Sun as Saturn moves along its orbit, and the seasonal tilt of the Moon's poles toward and away from solar illumination. To isolate the excess heat coming from the interior, the researchers had to model all of these external contributions with extreme precision and subtract them from the measured temperatures. What remained after that subtraction was the endogenic component, the heat leaking up from below. The team chose to analyze observations taken during the North Polar winter, when the pole was tilted away from the Sun and receiving no direct sunlight at all. During these periods, the only heat reaching the surface should have been the faint background warmth conducted through the ice from the distant ocean. By comparing predicted winter temperatures, calculated from thermal models that included every known external heat source, with the actual temperatures measured by Cassini's spectrometer, the researchers identified a persistent warm anomaly that could not be attributed to anything except internal heat flow. The signal was subtle, It was buried in data collected over a decade earlier, and it required analytical techniques that did not exist when Cassini was operational. The discovery was a reminder that spacecraft data can contain revelations that outlive the missions that collected them, waiting in archives for years or decades until someone asked the right question with the right tools. The measured heat flow at the North Pole came to approximately 46 milliwatts per square meter, plus or minus 4 milliwatts. To calibrate that number against something familiar, the average heat flow through Earth's continental crust is approximately 65 milliwatts per square meter. Enceladus's North Pole is radiating heat at roughly 2/3 the rate of a typical patch of Earth's continental surface. That comparison is startling. Earth is a massive planet with a molten interior, radioactive decay in its mantle, and residual primordial heat from formation. Enceladus is a frozen moon, 500 kilometers wide, yet the heat escaping through its north polar ice approaches continental scale values on Earth. When the north polar heat flow was added to the energy already measured from the south polar plumes and the surrounding terrain, the total heat output of Enceladus reached approximately 54 gigawatts. This number turned out to be remarkably close to theoretical predictions of how much tidal heat the Moon should be generating based on its orbital eccentricity and internal structure. The match was almost too good. It implied that Enceladus is in approximate thermal equilibrium. The heat being generated by tidal flexing is roughly equal to the heat being radiated away through the ice shell and the plumes. The energy budget balances. This equilibrium has profound implications. If Enceladus were generating far more heat than it could radiate, the ice shell would thin rapidly, and the Moon would undergo a runaway melting event. If it were radiating far more heat than it generated, the ocean would be freezing, and the plumes would be a temporary phenomenon destined to shut down. Neither scenario matches the observations. Instead, the near-perfect balance suggests that the current state of Enceladus, global ocean, active plumes, measurable heat flow at both poles, could be stable over very long timescales, potentially billions of years. The ocean is not a transient feature. It is not the last gasp of a dying world. It is a sustained, balanced, long-term environment maintained by a gravitational engine that shows no signs of stopping. The 2025 study also refined estimates of ice shell thickness. Based on the thermal modelling required to match the observed North Polar heat flow, the researchers estimated the ice at the North Pole to be roughly 20 to 23 kilometres thick. The global average came to approximately 25 to 28 kilometres. These numbers are slightly higher than some earlier models had suggested, but they remain consistent with the overall picture of a moon, whose ice shell is thinnest where heating is most intense, and thickest where the surface is most quiescent. The thickness of the ice shell matters because it determines how effectively heat can escape from the ocean to the surface. Thinner ice allows more heat to conduct through, potentially keeping the ocean warmer in those regions. Thicker ice insulates more effectively, trapping heat below. The variation in shell thickness creates a thermal geography beneath the surface, a landscape of warmer and cooler ocean regions that mirrors the variation in tidal heating intensity. The South Polar Ocean, beneath the thinnest ice, is likely the warmest part of the subsurface sea. The Equatorial and Northern Ocean, beneath thicker ice, may be cooler but still well above the freezing point of saltwater. This thermal structure also implies something important about ocean circulation. Temperature differences drive convection in any fluid body. Warmer water rises, cooler water sinks. If the South Polar Ocean is warmer than the Equatorial Ocean, there should be large-scale circulation patterns, moving water from the warm regions toward the cooler regions and back again. The ocean of Enceladus is not static. It is not a stagnant pool sitting passively beneath the ice. It is a dynamic, circulating body of water driven by the same tidal heating that keeps it liquid. Material from the ocean floor, from the water column, from every corner of this hidden sea, is continuously being mixed and redistributed by convection currents powered by the gravitational engine above. Imagine lighting a single candle beneath a frozen lake. The heat would melt a small pocket of water above the flame, but the warmth would also create convection currents, drawing cold water downward and pushing warm water outward. Over time, the entire lake would develop a circulation pattern driven by that single point of heat input. Now replace the candle with a distributed heat source covering the entire lake floor, strongest at one end and weaker at the other. The resulting circulation would be complex, persistent, and capable of transporting dissolved chemicals across the full extent of the water body. That is what is happening inside Enceladus. The tidal heating acts as a distributed energy source, strongest near the South Pole, weaker elsewhere, driving a global oceanic circulation that has been operating for potentially billions of years. The rocky core plays a critical role in this system. Unlike some other icy moons where the ocean is sandwiched between layers of ice, with high-pressure ice forming at the base, Enceladus's ocean sits directly on top of rock. The moon's gravity is too weak, and the ocean is not deep enough to produce the pressures required for high-pressure ice phases. This means the liquid water is in direct contact with silicate rock across the entire ocean floor, water touching rock, for billions of years. With heat being continuously supplied from below, on Earth, the places where hot water interacts with rock on the ocean floor are called hydrothermal vents. These environments support thriving ecosystems of microbial life and complex organisms entirely independent of sunlight. The energy comes from chemical reactions between water and rock, reactions that produce hydrogen, sulfides, and other reduced compounds that microorganisms can use as fuel. The discovery that Enceladus has a rocky ocean floor in direct contact with heated saltwater immediately drew comparisons to these terrestrial environments. Several lines of evidence support the existence of active hydrothermal processes on Enceladus's ocean floor, including the detection of nanoscale silica particles and molecular hydrogen in the plume material. The full significance of these chemical detections would emerge over years of analysis and reanalysis, building a portrait of ocean floor conditions that no one had imagined finding on a moon this small. The silica nanoparticle story deserves its own telling, because the chain of reasoning behind it is one of the most elegant pieces of detective work in modern planetary science. In 2015, a team led by Xiangwen Xu at the University of Colorado published a study tracing the origin of nanoscale silica grains found in Saturn's E-ring. These particles were tiny, between 6 and 9 nanometers in diameter, and composed almost entirely of silicon dioxide. On Earth, silica particles of this specific size range form through only one known mechanism: when hot water saturated with dissolved silica encounters a sudden drop in temperature, the silica precipitates out of solution as ultrafine grains. The speed of cooling determines the grain size. Slow cooling produces large crystals. Rapid cooling produces nanoparticles. The 6 to 9 nanometer size range corresponds to water temperatures of at least 90 degrees Celsius, dropping rapidly to near-freezing conditions. This temperature constraint was revelatory. It meant that somewhere on the ocean floor of Enceladus, water was being heated to at least 90 degrees Celsius through contact with rock, dissolving silica from the mineral surfaces, and then rising rapidly into cooler ocean water where the silica precipitated out as nanoparticles. The particles were then entrained in the upwelling currents that feed the plumes, carried through the tiger stripe fractures, and ejected into space along with everything else. From there, they entered Saturn's E-ring, where Cassini's CDA caught them and measured their composition and size. The entire chain, from hydrothermal vent to E-ring, spans a journey of hundreds of kilometers vertically and hundreds of thousands of kilometers horizontally. Yet the nanoparticles survived intact, retaining their diagnostic size throughout the process. Their presence in the ring was a message sent from the ocean floor of Enceladus, through the ice, across the vacuum of space, and into the instrument of a spacecraft that happened to be in the right place at the right time to intercept it. It was a message that said, "There is hot water touching rock at the bottom of this ocean right now, as you hear this data." Additionally, Cassini detected molecular hydrogen in the plume during its deepest dive through the eruption column in 2015. Molecular hydrogen in this context was a powerful clue. It implied an active chemical conversation between the ocean and the rock beneath it, a process whose full significance would become clear as scientists pieced together the broader chemical story the plumes were telling. The hydrogen was not a leftover from formation. It was being freshly produced, right now, by reactions unfolding on the ocean floor of a moon nearly 1 billion miles from the Sun. The picture that emerged from 13 years of Cassini data and subsequent analysis is unlike anything planetary scientists had imagined before the mission. Enceladus is not a frozen relic. It is not a dead moon with a residual warm spot. It is a fully active ocean world with a global liquid water ocean maintained by continuous tidal heating, in approximate thermal equilibrium between heat generation and heat loss, with a rocky ocean floor where hot water interacts with silicate rock in processes directly analogous to the hydrothermal systems that sustain life on Earth. The ocean circulates, the chemistry evolves. Climbed, the heat persists, and the evidence for all of it is being delivered directly into space through plumes that any future spacecraft can fly through and sample. Supercomputer simulations published in November 2025 further refined understanding of the plume dynamics. Cutting-edge models showed that Enceladus's plumes are losing approximately 20 to 40% less mass than earlier estimates had suggested. The revised calculations mean that the plume material is moving through the fractures more efficiently than previously thought, with less energy being wasted on heating the walls of the tiger stripe channels. This has implications for how scientists interpret the chemistry of the plume samples. If the material spends less time interacting with the ice walls during its ascent, the chemical composition of the ejected grains may more faithfully represent the ocean below. The plumes may be even more reliable windows into the subsurface chemistry than researchers had assumed. This realization transforms the plumes from a spectacular geological curiosity into something far more important. They are a pipeline, a direct conduit from a hidden ocean to open space. No drilling required, no landing necessary. The plumes transform the scientific problem entirely. Before Cassini, studying a subsurface ocean on any world meant imagining distant future missions with capabilities that did not yet exist. After Cassini, studying the ocean of Enceladus meant catching what the moon was already throwing into space. The ice grains in those plumes carried chemical fingerprints from the water below. The vapor carried dissolved gases from the deep interior. Every eruption was a free transmission of information from a hidden sea, broadcast into open space for anyone with the right instruments to decode. And what those samples contain has turned this tiny moon from a geological surprise into one of the most chemically extraordinary objects ever studied. Most ocean worlds in the solar system keep their secrets locked away. Whatever chemistry is unfolding beneath the ice of Europa or deep inside the interior of Ganymede stays hidden under kilometers of frozen crust, inaccessible to any instrument humanity currently possesses. To study those oceans, you would need to land on the surface, drill through a shell of ice thicker than the Earth's crust is deep in most places, deploy a submersible into the liquid below, and somehow transmit the results back across hundreds of millions of miles of space. The engineering challenges are staggering. The cost is measured in decades and tens of billions of dollars. And even then, you would be sampling a single point in a vast ocean, hoping that whatever your probe encounters is representative of the whole. Enceladus eliminated every single one of those problems in a single stroke. Its plumes are carrying ocean material up through fractures in the ice shell, accelerating it past the moon's escape velocity, and delivering it into open space where any passing spacecraft can collect it. The ocean is coming to you. The chemistry is on display. The evidence is being broadcast continuously into Saturn's orbital environment at a rate that sustains an entire planetary ring. No drilling, no landing, no submersible. Just fly through the plume and catch what comes out. Cassini did exactly that, multiple times. And what it found in those plume samples reshaped the entire scientific conversation about where life might exist in the solar system. The first and most fundamental detection was water. The plumes are overwhelmingly composed of water vapor, which was expected given that the source is a saltwater ocean beneath water ice. But confirming that the erupted material was genuinely oceanic in origin, rather than surface ice being sublimated by solar heating, required more than just detecting water molecules. The critical evidence came from the ice grains. Cassini carried an instrument called the Cosmic Dust Analyzer, or CDA, designed to capture individual microscopic particles and determine their composition through impact ionization mass spectrometry. When a tiny ice grain traveling at several kilometers per second strikes a metal target inside the instrument, the impact vaporizes and ionizes the grain, producing a cloud of charged atoms and molecules that can be sorted by mass. Each grain produces a unique chemical fingerprint, revealing what it was made of before it was destroyed. The CDA analysed thousands of individual ice grains ejected from the tiger stripe fractures. The results fell into three broad categories that told a layered story about the ocean below. The first and most common type consisted of nearly pure water ice, with trace amounts of organic material. These grains likely formed when relatively clean ocean water flash froze as it entered the vacuum of the tiger stripe vents. The second type was dramatically different. These grains were rich in sodium chloride and potassium chloride at concentrations between 0.5% and 2% by mass. The salinity fell within the same order of magnitude as Earth's oceans, roughly 0.5% to 2% by mass compared to Earth's 3.5%. These salt-rich grains could not have formed from the sublimation of surface ice. Surface ice on Enceladus is nearly pure water. Salt-bearing ice grains can only form from the freezing of liquid salt water. Their presence was among the earliest and strongest pieces of evidence that the plume material was coming directly from a liquid ocean in contact with rock. The salts themselves, sodium and potassium in particular, are products of prolonged water-rock interaction. They dissolve out of silicate minerals over time as water circulates through rocky material. Finding them in the plume meant the ocean had been touching rock long enough for significant mineral dissolution to occur. The third category of ice grains was the most intriguing. These particles contained complex organic molecules with masses exceeding 200 daltons. Some fragments suggested even larger parent molecules with masses potentially reaching thousands of daltons. On Earth, molecules in this mass range include amino acids, fatty acids, and other compounds associated with biological processes. Cassini's instruments were not sensitive enough to identify the exact molecular structures, but the mass spectra indicated compounds with both oxygen-bearing and nitrogen-bearing functional groups, hallmarks of the kind of chemistry that underpins biology. The detection of complex organics in the plume did not prove that life exists in Enceladus's ocean. Organic molecules form through abiotic processes throughout the solar system. Comets carry them. Asteroids contain them. Titan's atmosphere produces them in staggering quantities through photochemistry driven by ultraviolet radiation. The presence of organics means that the raw materials for life are available. It does not mean those materials have been assembled into living systems, but the specific context in which these organics were found, dissolved in or associated with salty liquid water erupting from an ocean with an active energy source, placed them in a category entirely different from organics found on a comet or in a cold asteroid. These molecules were being produced or processed in an environment that shares fundamental characteristics with the places where life thrives on Earth. Cassini's other plume sampling instrument, the Ion and Neutral Mass Spectrometer, or INMS, provided complementary data on the gas phase composition of the plume. Water vapor dominated, as expected. But the spectrometer also identified carbon dioxide, methane, ammonia, molecular hydrogen, formaldehyde, and trace quantities of heavier organic species. Each of these detections carried specific implications for conditions inside the ocean. Ammonia is significant because it acts as an antifreeze in water. Its presence lowers the freezing point of the ocean, allowing liquid water to persist at temperatures below 0 degrees Celsius. Ammonia also affects the pH of the solution, making it more alkaline. Combined with the salt concentrations measured by the CDA, the emerging picture was of an ocean with a pH between roughly 8 and 11, mildly to moderately alkaline, similar to soapy water or certain alkaline lakes on Earth. This pH range is hospitable to many forms of terrestrial microbial life, including organisms that thrive in alkaline hydrothermal environments. Carbon dioxide and methane provided windows into carbon chemistry within the ocean. Carbon dioxide dissolves readily in water and participates in carbonate chemistry, the same system that regulates ocean acidity on Earth. Methane can be produced through several mechanisms, including abiotic reactions between carbon dioxide and molecular hydrogen at hydrothermal temperatures, a process called Fischer-Tropsch synthesis, or through the metabolic activity of methanogenic microorganisms. Distinguishing between abiotic and biotic methane sources is one of the great unsolved problems in Enceladus science. Both pathways are plausible given the known conditions, and Cassini's instruments lacked the resolution to measure the isotopic ratios that might discriminate between them. Molecular hydrogen deserves special attention because its implications are so far-reaching. Cassini detected molecular hydrogen during its deepest plume dive in October 2015, passing within 49 kilometers of the south polar surface. The concentration was higher than could be explained by the simple decomposition of water molecules by radiation. The most likely source was an ongoing chemical reaction between liquid water and iron-bearing minerals in the rocky core, a process called serpentinization. Serpentinization occurs when water infiltrates cracks in certain types of rock, particularly rocks rich in the minerals olivine and pyroxene. The water reacts with iron in these minerals, oxidizing it from a reduced state to an oxidized state. In the process, hydrogen gas is liberated. The reaction is exothermic, generating heat that supplements whatever tidal energy is already warming the interior. On Earth, serpentinization is one of the primary chemical engines driving hydrothermal vent ecosystems on the ocean floor. The hydrogen it produces serves as an energy source for chemosynthetic microorganisms, bacteria and archaea that harvest the chemical energy in hydrogen to drive their metabolism, completely independent of sunlight. Finding molecular hydrogen in Enceladus's plume was equivalent to finding smoke rising from a chimney. It did not prove there was a fire, but it proved there was heat, there was fuel, and there was an active chemical process capable of sustaining one. The energy implications of serpentinization are worth pausing over because they address one of the most fundamental requirements for any living system. Life requires not just ingredients but a thermodynamic gradient, a difference in chemical potential that organisms can exploit to do metabolic work. On Earth's surface, the dominant gradient is between sunlight and the chemical environment. Photosynthetic organisms capture solar energy and use it to build organic molecules from carbon dioxide and water. Virtually every ecosystem on the planet's surface depends, directly or indirectly, on this solar energy input. But in the perpetual darkness of Earth's deep ocean floor, where volcanic rock meets frigid seawater, a completely different energy economy operates. There, the gradient is chemical rather than solar. Hot, hydrogen-rich water flowing out of the vents encounters cold, carbon dioxide-rich ocean water. The chemical disequilibrium between these two fluids represents stored energy that microorganisms can harvest. Methanogenic archaea, some of the most metabolically simple organisms known, combine molecular hydrogen with carbon dioxide to produce methane and water, extracting just enough energy from the reaction to sustain their cellular processes. These organisms require no sunlight, no oxygen, no organic food source. They live on rock, water, and chemistry alone. The detection of molecular hydrogen in Enceladus's plume established that this same type of chemical gradient exists in the Moon's ocean. Hydrogen is being produced at the ocean floor through serpentinization. Carbon dioxide is present in the water, as confirmed by Cassini's INMS measurements. The two reactants are available. The thermodynamic gradient exists. Whether any organism has ever exploited that gradient is unknown, but the gradient itself, the energy source, the fuel, is confirmed. Enceladus's ocean is not merely a body of water with interesting chemistry. It is a body of water with a confirmed energy supply capable of powering the simplest known forms of life on Earth. The fuel is there. The engine could run. Whether it has ever been switched on is the question a return mission would attempt to answer. If methanogenic archaea, among the most ancient and metabolically simple organisms on Earth, were placed in the conditions inferred for Enceladus's ocean floor, they would have everything they need to survive. Liquid water, chemical energy from hydrogen, carbon dioxide as a carbon source, mineral surfaces for attachment and warmth. The environment is not merely theoretically habitable, it is operationally habitable by the standards of known terrestrial biology. But the chemical inventory of the plume was not yet complete. In June 2023, a team led by Frank Postberg at the Free University of Berlin published a result in the journal Nature that added the final element to a list scientists had been assembling for years. By reanalyzing archived CDA data from Cassini's passages through Saturn's E-ring, the ring fed and maintained by Enceladus's plumes, the researchers identified sodium phosphate in the ice grains. Phosphorus, the sixth and last of the elements universally required by life as we know it. Every living cell on Earth depends on 6 elements. Carbon provides the structural backbone of organic molecules. Hydrogen and oxygen compose water and participate in nearly every biochemical reaction. Nitrogen is essential for amino acids and nucleic acids. Sulfur plays critical roles in protein structure and enzyme function. And phosphorus is the backbone of DNA and RNA, the energy currency of the cell in the form of adenosine triphosphate, and a major structural component of cell membranes. Without phosphorus, there is no genetic information storage, no energy transfer, no cellular structure as biology understands it. For years, phosphorus had been the missing piece. Cassini had detected carbon, hydrogen, nitrogen, oxygen, and sulfur in the plume, 5 out of 6. But phosphorus had eluded detection, and its absence nagged at astrobiologists. Some researchers worried that Enceladus's ocean might be phosphorus poor, which would severely limit its habitability regardless of all the other favourable conditions. The 2023 detection eliminated that concern. Phosphorus was there. It was dissolved in the ocean water at concentrations estimated to be at least 100 times higher than in Earth's oceans. The ocean of Enceladus contains all 6 elements that life requires, dissolved in liquid salt water, in an environment with active chemical energy sources and sustained warmth. The phosphorus story had been building for years before the 2023 announcement. After Cassini confirmed the presence of carbon, hydrogen, nitrogen, oxygen, and sulfur in the plume material, astrobiologists began referring to the collection as 5 out of 6. The phrase carried an undertone of anxiety. 5 out of 6 was extraordinary. 5 out of 6 was unprecedented for any world beyond Earth. But 5 out of 6 was also incomplete, and the missing element was not a minor player. Phosphorus occupies a position in biochemistry that no other element can fill. The backbone of every DNA and RNA molecule is a chain of phosphate groups linked by sugar molecules. Without phosphorus, there is no genetic code, no heredity, no evolution. The primary energy currency of all known cells, adenosine triphosphate, contains 3 phosphate groups whose chemical bonds store and release the energy that drives virtually every cellular process. Cell membranes are built from phospholipids, molecules with phosphate head groups that self-assemble into the bilayer sheets enclosing every living cell. Remove phosphorus from the equation, and the entire architecture of life as understood by biology collapses. There is no known alternative, no workaround, no substitute element that can perform the same functions. This is why the absence of a phosphorus detection weighed so heavily on the community. Some researchers published models suggesting that Enceladus's ocean might be inherently phosphorus poor. In certain geochemical scenarios, phosphorus binds tightly to calcium and iron in the rock, forming insoluble mineral phases that lock it away from the liquid water. If the ocean floor chemistry was sequestering phosphorus rather than releasing it, the ocean might contain water, salts, organics, energy, and 5 of the 6 essential elements, yet still be fundamentally uninhabitable because the 6th was locked in the rock. The 2023 result demolished that concern so completely that it almost overcompensated. The phosphorus concentrations measured in the E-ring ice grains implied ocean levels at least 100 times higher than Earth's seawater. Enceladus did not merely have phosphorus, it was swimming in it. The geochemical models that predicted phosphorus scarcity turned out to be based on assumptions about ocean chemistry that did not apply to Enceladus's alkaline, carbonate-rich conditions. In this specific chemical regime, phosphorus remains highly soluble. The ocean floor was not locking phosphorus away, it was dissolving it into the water at rates that produced concentrations far beyond anything found in terrestrial oceans. The missing element was not missing at all, it was abundant, and with its detection, the chemical inventory of Enceladus's ocean crossed a threshold. Every element that life requires, without exception, was confirmed present in a single extraterrestrial ocean. The concentration of phosphorus was itself remarkable. On Earth, phosphorus is often the limiting nutrient for biological productivity. It is scarce in seawater because it tends to bind tightly with calcium and precipitate out of solution as insoluble minerals. The fact that Enceladus's ocean contains phosphorus at such high concentrations suggests that the ocean chemistry differs from Earth's in ways that keep phosphorus in solution. One possibility is that the alkaline, carbonate-rich conditions of the Enceladian ocean prevent phosphorus from precipitating. Another is that ongoing dissolution of phosphorus-bearing minerals on the ocean floor continuously replenishes the supply. Either way, the ocean appears to be not merely phosphorus-bearing, but phosphorus-rich, removing what had been considered one of the most serious potential obstacles to habitability. 6 months after the phosphorus announcement, in December 2023, another team published results identifying hydrogen cyanide and several previously undetected organic compounds in the plume. Hydrogen cyanide is a molecule of enormous significance in prebiotic chemistry. Despite being a lethal poison to complex aerobic organisms on Earth, hydrogen cyanide is considered one of the most important precursor molecules for the synthesis of amino acids, nucleic acid bases, and other building blocks of life. Laboratory experiments dating back to the 1950s have demonstrated that hydrogen cyanide in water, combined with energy input, can produce amino acids, purines, and pyrimidines through well-understood chemical pathways. Finding hydrogen cyanide in Enceladus's plume suggested that the ocean contains the raw ingredients for prebiotic chemistry, the kind of chemistry that may have preceded the origin of life on Earth. The pace of discovery did not slow after Cassini's mission ended. In October 2025, a team at the European Space Agency published results from a fresh reanalysis of archived Cassini CDA data. Using improved data processing techniques unavailable during the primary mission, the researchers identified new complex organic molecules in the ice grains. These molecules strengthen the case that the ocean of Enceladus hosts sustained chemical processing capable of producing compounds relevant to biology. The specific molecular structures remain under investigation, but the mass spectra point to compounds with carbon-nitrogen bonds and oxygen-bearing functional groups, precisely the types of chemical features found in amino acids and other biologically relevant molecules. But science requires skepticism, and not every interpretation of the plume chemistry has gone unchallenged. In September 2025, a study presented at the Europlanet Science Congress raised an important cautionary note. The researchers argued that some of the organic molecules detected in Enceladus's plumes could have been produced by radiation processing at or near the Moon's surface rather than originating from the deep ocean. Saturn's magnetosphere bathes Enceladus in energetic charged particles. When these particles strike ice containing simple organic precursors, they can drive chemical reactions that produce more complex molecules. If this surface radiolysis is contributing significantly to the plume chemistry, then some of the organic detections might not reflect ocean conditions at all. They might reflect surface processes that have nothing to do with habitability. This is a legitimate scientific concern, and it has not been fully resolved. However, several lines of evidence suggest that surface radiolysis cannot account for the bulk of the organic material in the plume. First, the salt-rich ice grains containing organics are compositionally consistent with an oceanic origin. Surface ice on Enceladus is nearly salt-free. Finding salts and organics together in the same grains strongly implies they were both dissolved in liquid water before being ejected. Second, the molecular masses of some detected organics exceed what typical radiolysis experiments produce from simple ice mixtures. The complexity of the molecules points towards sustained liquid phase chemistry rather than brief radiation-driven reactions on a frozen surface. Third, the plume material erupts from fractures connected to a subsurface liquid reservoir. The physical pathway favors deep-sourced material over surface contamination. The debate is healthy and ongoing. It represents science functioning as it should, testing every interpretation against alternative explanations, demanding that extraordinary claims meet extraordinary standards of evidence. But the weight of the evidence accumulated over nearly 2 decades of analysis tilts heavily toward the conclusion that most of what Cassini caught in the plume came from the ocean, and what the ocean contains is a chemical environment strikingly similar to the hydrothermal systems where some origin of life researchers believe terrestrial biology first emerged. In January 2026, laboratory experiments published in the journal Icarus took the investigation in a complementary direction. Rather than analyzing Cassini data, a team of researchers attempted to recreate the conditions of Enceladus's subsurface ocean in the laboratory. They prepared chemical mixtures based on the simple compounds Cassini had detected in the plume, including ammonia and hydrogen cyanide, and subjected them to cycles of heating and cryogenic freezing inside high-pressure reactors, mimicking the tidal heating cycles the Moon experiences each orbit. The experiments produced more complex organic compounds from simpler precursors, demonstrating that the physical conditions inside Enceladus are sufficient to drive organic chemistry forward toward greater complexity without any biological intervention. This result matters because it closes a gap in the argument. Detecting complex organics in the plume proves they exist, but it does not prove they were made in the ocean. They could conceivably have been delivered by cometary material during impacts early in solar system history and simply preserved in the ice. The laboratory experiments showed that the conditions inside Enceladus are independently capable of producing complex organics from scratch through abiotic hydrothermal chemistry. The ocean is not merely storing organic molecules, it is manufacturing them continuously through processes driven by the same tidal energy that keeps the water liquid. The laboratory work deserves closer examination because it tested a specific and important question. If you start with the simple molecules Cassini detected in the plume, ammonia, hydrogen cyanide, carbon dioxide, methane, and you subject them to the physical conditions believed to exist inside Enceladus, do you get more complex molecules out? Or do the simple ingredients remain simple, sitting inertly in water without reacting further? The research team, led by Maxwell Craddock, built a high-pressure reactor designed to simulate the environment of Enceladus's ocean floor. They prepared aqueous solutions containing the simple compounds at concentrations consistent with Cassini's measurements. They then sealed these solutions inside the reactor and subjected them to repeated cycles of heating and cooling, mimicking the periodic tidal flexing that Enceladus experiences each orbit. The heating phases raised temperatures to ranges consistent with hydrothermal conditions. The cooling phases dropped temperatures back toward ambient ocean levels. Each cycle lasted hours, and the experiment ran through dozens of cycles to simulate extended exposure to tidal-driven thermal variation. The results were unambiguous. After multiple heating-cooling cycles, the solutions contained organic compounds significantly more complex than the starting materials. Hydrogen cyanide, one of the most reactive molecules in prebiotic chemistry, had polymerized and reacted with other dissolved species to produce larger nitrogen-bearing organic molecules. Ammonia had participated in reactions forming compounds with carbon-nitrogen bonds. The complexity of the product mixture increased with the number of cycles, suggesting that each round of tidal heating drove the chemistry one step further along the path from simple to complex. The experiment did not produce life. Nobody expected it to. But it demonstrated that the conditions inside Enceladus are sufficient to drive the kind of progressive chemical complexification that prebiotic chemists consider a necessary precursor to the origin of life. The Moon's ocean is not a static reservoir of ingredients waiting for something to happen. It is an active chemical reactor, cycling its contents through temperature gradients driven by the same gravitational engine that keeps the water liquid, and the reactions are running. Taken together, the chemical portrait of Enceladus's ocean, assembled from nearly 2 decades of data analysis, laboratory work, and computational modeling, is unlike anything found elsewhere in the solar system outside of Earth. Consider what has been confirmed or strongly inferred: a global ocean of liquid salt water with a pH in the alkaline range. All 6 elements essential for life, including phosphorus at concentrations far exceeding those in Earth's oceans. Complex organic molecules with masses in the hundreds of daltons being produced through active chemical processing. Molecular hydrogen generated by ongoing serpentinization reactions between water and rock on the ocean floor. Silica nanoparticles indicating hydrothermal temperatures near 90 degrees Celsius at the water-rock interface. Hydrogen cyanide and other prebiotic precursors available for organic synthesis. And a sustained energy source, tidal heating, maintaining these conditions potentially across billions of years. No individual detection proves that life exists in the ocean of Enceladus. Each piece of evidence has alternative abiotic explanations. Molecular hydrogen can be produced without biology. Complex organics can form without cells. Phosphorus can dissolve into water that never touches a living organism. But the convergence of all these factors in a single environment is what makes Enceladus extraordinary. It is not one favorable condition. It is all of them, simultaneously, in a self-sustaining system that has the thermal stability to persist across geological time. On Earth, the hydrothermal vents on the deep ocean floor support ecosystems that function in complete independence from the sun. No photosynthesis, no atmospheric oxygen, just hot water, dissolved minerals, chemical gradients, and microbial communities that extract energy from the reactions between water and rock. These organisms are among the most ancient lineages on Earth's tree of life. Some researchers believe they represent the closest modern analogues to the first living cells that emerged on this planet roughly 4 billion years ago. The conditions at those vents, hot alkaline water rich in hydrogen and carbon dioxide flowing over mineral-laden rock, are essentially identical to the conditions inferred for the ocean floor of Enceladus. This does not mean life is there. It means that if you were designing an experiment to test whether life could arise on another world, Enceladus would be the control case. It has every ingredient, it has every condition. It has the energy, the chemistry, the water, and the time. What it may or may not have is the spark. The unknown factor that transforms chemistry into biology. Whether that spark requires something beyond favourable conditions, something rare or unique about Earth's early environment, or whether it is an inevitable consequence of the right ingredients persisting for long enough, remains one of the deepest unanswered questions in science. The plumes have transformed Enceladus from a geological curiosity into something far more consequential. They are not merely evidence of internal activity, they are a chemical resume, a continuous broadcast of the ocean's composition beamed into space for any sufficiently advanced civilization or sufficiently capable spacecraft to read. Every molecule in every ice grain is a data point. Every gas phase detection is a constraint on ocean chemistry. Every new analysis of archived Cassini data reveals another line on that resume. Another reason to take this tiny moon seriously as a potential harbour for the kind of chemistry that, on at least one world, crossed the threshold into life. And the most unsettling part of the story is not what the plumes have already revealed, it is what they have not. Cassini was never designed to search for life at Enceladus. Its instruments were built for a general-purpose survey of the Saturn system, optimized for a broad range of scientific objectives. The mass spectrometers that sampled the plume had resolution limits that prevented identification of specific amino acids. The dust analyzer could determine bulk composition but could not distinguish between left-handed and right-handed molecular structures, a distinction that is one of the most reliable indicators of biological origin. Cassini gave us enough information to know that Enceladus's ocean is chemically extraordinary. It did not give us enough to determine whether that chemistry has crossed the line into biology. That determination requires a return mission, a spacecraft built specifically for the question. And the scientific community knows it. The plumes are waiting. The ocean is broadcasting, and the chemistry written in those ice grains may contain an answer that would change everything humanity understands about its place in the universe. For most of the history of planetary science, the solar system was sorted into categories that felt permanent. The rocky inner planets were the interesting ones. Mercury, Venus, Earth, and Mars occupied the zone where sunlight was strong enough to matter, where surfaces were warm enough for dynamic geology, where atmospheres could develop and evolve. Beyond the asteroid belt lay the gas giants, impressive in scale but fundamentally alien. Worlds of hydrogen and helium without solid surfaces, orbited by retinues of moons that were assumed to be frozen, inert, and scientifically unremarkable. This framework made intuitive sense. Heat drives activity, sunlight provides energy, distance from the sun determines temperature. The farther out you go, the less interesting things should be. Enceladus destroyed that framework. A moon 500 kilometers wide, orbiting at 9.5 astronomical units from the sun, receiving roughly 1% of the solar energy that falls on Earth, has turned out to be one of the most chemically complex, geologically active, and astrobiologically significant objects ever studied. It possesses a global ocean of liquid salt water. It contains every element that life requires. It produces complex organic molecules through active hydrothermal chemistry. It vents its ocean contents directly into space through over 100 geysers. And it maintains all of these conditions through a gravitational heating mechanism that may have been operating for billions of years. Nothing about this was predicted. Nothing about it was expected. and the fact that it took until 2005 for anyone to notice tells us something uncomfortable about the assumptions that governed planetary science for the better part of a century. The assumption was that size determines significance. A large world can hold on to heat, sustain an atmosphere, drive plate tectonics, maintain a magnetic field. A small world cannot. This principle is broadly correct. Mars is geologically dead because it is too small to retain internal heat. The Moon is geologically dead for the same reason. Mercury is geologically dead. Every small rocky body in the inner solar system confirms the pattern. Size matters. Small equals dead. But Enceladus revealed the fatal flaw in this reasoning. The principle was derived entirely from worlds where the only energy source is primordial heat and radioactive decay. It did not account for tidal heating. It did not account for the possibility that a tiny moon locked in gravitational resonance with a neighboring satellite, orbiting close to a massive gas giant, could receive a continuous supply of energy from an external source that has nothing to do with size, nothing to do with sunlight, and nothing to do with the moon's own internal composition. Tidal heating changes the rules. It means a moon the size of a large asteroid can sustain conditions that would otherwise require a body thousands of kilometers across. The second assumption Enceladus shattered was that distance from the Sun determines habitability. The habitable zone, the orbital band around a star where liquid water can exist on a planet's surface, has been one of the most influential concepts in astrobiology. Earth sits squarely within the Sun's habitable zone. Mars lies near the outer edge. Venus lies near the inner edge. For decades, the search for potentially habitable worlds focused almost exclusively on finding planets in this narrow band where surface temperatures allow liquid water. Everything else was considered too hot or too cold. Enceladus demonstrated that liquid water can exist nearly 1 billion miles from the Sun, far beyond any reasonable definition of the habitable zone, as long as an alternative energy source is available. The habitable zone concept remains useful for identifying worlds with surface oceans warmed by starlight, but it fails catastrophically when applied to subsurface oceans warmed by tidal forces. The ocean of Enceladus does not care how far it is from the Sun. It is heated from below by the gravitational relationship between the Moon, Saturn, and Dione. Sunlight is irrelevant. Distance is irrelevant. What matters is the gravitational architecture of the system, and that architecture can produce habitable conditions in places that no one was looking. This realization expanded the potential territory for life in the universe by an almost incomprehensible margin. Every gas giant in every stellar system potentially harbors icy moons with tidal heating. Jupiter has 4 large Galilean satellites, at least 2 of which, Europa and Ganymede, are confirmed to possess subsurface oceans. Saturn has Enceladus and possibly Titan, whose subsurface water ocean is suspected but less well characterized. Neptune's moon Triton shows signs of cryovolcanic activity. Even dwarf planets and large Kuiper belt objects may harbor internal oceans maintained by residual heat or tidal interactions. The number of potential ocean worlds in our solar system alone may exceed 12. Extrapolate that to the trillions of planetary systems in the Milky Way, each potentially hosting gas giants with icy moons in resonant orbital configurations, and the number of possible habitable environments becomes staggering. But among all these candidate ocean worlds, Enceladus holds a unique position. It is the only one that offers direct access to its ocean without drilling. Europa is often cited as the leading candidate for extraterrestrial life in the solar system, and for good reason. It is larger than Enceladus, roughly 3,100 kilometers in diameter. Its ocean is estimated to contain roughly 2 to 3 times the volume of all of Earth's oceans combined. It has a rocky ocean floor, a source of tidal heating from Jupiter, and tentative evidence for plume activity observed by the Hubble Space Telescope. NASA's Europa Clipper mission, launched in October 2024, is scheduled to arrive at Jupiter in April 2030 to conduct detailed flybys and characterize Europa's ice shell, ocean, and potential habitability. Europa is a compelling target, but it has a significant disadvantage compared to Enceladus. Europa's ice shell is estimated at 19 to 25 kilometers thick across most of its surface. Accessing the ocean directly would require technology that does not yet exist. a robotic probe capable of melting or drilling through a shell of ice deeper than the average depth of Earth's continental crust. The plume activity detected at Europa remains tentative and sporadic. If plumes exist, they appear far less vigorous than those at Enceladus, producing far less material and operating intermittently rather than continuously. Europa Clipper may confirm or refute the presence of plumes during its mission, but even if plumes exist, they may not provide the same quality of ocean sampling that Enceladus offers. Enceladus, by contrast, is broadcasting continuously. Over 100 geysers are ejecting ocean material into space at rates that sustain an entire ring of Saturn. The plumes have been active for at least the duration of Cassini's 13-year mission at Saturn, and almost certainly far longer, given that the E-ring they sustain is a persistent feature requiring continuous replenishment. A spacecraft designed specifically to fly through these plumes with modern analytical instruments could collect ocean samples on every pass, building a comprehensive chemical and isotopic profile of the subsurface sea without ever touching the surface. The scientific community recognized this opportunity in the 2022 Planetary Science Decadal Survey, the once-per-decade report in which leading researchers identify the highest priority missions for the coming years. The survey recommended the Enceladus Orbiter as the second highest priority new flagship mission, behind only the Uranus orbiter and probe. The Orbiter concept envisions a spacecraft that would first orbit Enceladus, flying through the plumes repeatedly to collect and analyze ejected material, and then land near the South Polar region to study plume fallout deposited on the surface. The mission would carry instruments specifically designed to answer the question that Cassini could not: is there life in the ocean of Enceladus? The instruments under consideration for a mission like this represent a generational leap beyond what Cassini carried. High-resolution mass spectrometers could identify individual amino acids and determine whether they exhibit chirality, the preferential handedness that is one of the most reliable indicators of biological origin. On Earth, all life uses left-handed amino acids exclusively. A racemic mixture, equal parts left-handed and right-handed, indicates abiotic chemistry. A strong excess of one-handedness would be a powerful biosignature, circumstantial evidence that biological processes have been selecting and concentrating specific molecular forms. Cassini could not make this measurement. A dedicated Enceladus mission could. Each proposed instrument targets a different facet of the question, and the reason for this redundancy is deliberate. Claiming the discovery of extraterrestrial life would be the most extraordinary scientific assertion in human history. The standard of evidence cannot be a single ambiguous measurement. It must be a convergence of independent lines of evidence, each pointing to the same conclusion, each ruling out a different category of false positive. Consider the chirality measurement in more detail. Amino acids produced by abiotic chemistry form in equal mixtures of left-handed and right-handed versions. A racemic sample is the chemical signature of randomness, of molecules assembling without biological selection. But life on Earth uses only left-handed amino acids. Every protein in every cell on this planet is built exclusively from left-handed building blocks. If a mass spectrometer flying through Enceladus's plume detected amino acids with a strong excess of one-handedness, it would be very difficult to explain without invoking biology. Abiotic processes do not preferentially select one mirror image over another, biology does. But even a strong chiral excess would not be proof on its own. Unusual mineral surfaces can catalyze slight asymmetries under specific conditions. A single anomalous measurement could be debated for decades. This is why the mission concept layers multiple independent detection methods. The fluorescence microscope would search for cell-like structures in captured ice grains, particles with defined boundaries, internal compartmentalization, and dimensions consistent with microbial cells. Finding such structures alongside chirally excess amino acids would be far more compelling than either detection alone. The isotopic measurements would add yet another dimension. If carbon in the organic molecules shows the same kind of fractionation that biological metabolism produces on Earth, lighter carbon-12 enriched relative to carbon-13, that pattern combined with structural and chemical evidence would build a case that no single alternative explanation could easily dismiss. The point is not that any one instrument would answer the question. The point is that the plumes provide enough material, in sufficient quantity, with sufficient chemical diversity that a properly equipped spacecraft could subject that material to half a dozen independent tests simultaneously. No other target in the solar system offers this combination of accessibility and analytical opportunity. The answer may be there. The technology to extract it exists. The only missing ingredient is the mission itself. Other proposed instruments include fluorescence microscopes, capable of detecting cell-like structures in plume residue, nanopore sequencers that could identify polymer chains resembling genetic material, and high-sensitivity gas chromatographs that could measure the isotopic ratios of carbon and hydrogen in methane and other organic compounds. Carbon isotope ratios are particularly diagnostic. Biological processes on Earth preferentially use the lighter carbon-12 isotope, producing organic matter that is depleted in carbon-13 relative to inorganic carbon sources. If the methane or organic compounds in the plume show a similar isotopic fractionation, it would be strong evidence for biological metabolism. No single measurement would prove the existence of life. The standard of evidence for such a claim would be extraordinarily high, requiring multiple independent lines of evidence pointing to the same conclusion, while ruling out all plausible abiotic alternatives. But the plumes of Enceladus provide a sample source so rich, so accessible, and so directly connected to the subsurface ocean that the question is genuinely answerable with technology that exists today. The challenge is not scientific, it is logistical and political. Building, launching, and operating a flagship mission to Saturn requires years of development, billions of dollars in funding, and sustained institutional commitment across multiple government administrations. The earliest realistic launch window for an Enceladus mission is the mid-2040s, with arrival in the mid-2050s. The scientists who championed this mission during Cassini's operational years may not live to see its results, but the plumes will still be there. The ocean will still be circulating. The chemistry will still be broadcasting. Enceladus is not going anywhere. Its tidal heating engine is sustained by orbital mechanics that operate on timescales of billions of years. The resonance with Dione is stable. Saturn's gravity is constant. The flexing continues. The heat persists. The ocean endures. Whatever is happening beneath that ice has been happening for an almost inconceivable span of time and will continue long after every spacecraft humanity has ever launched has ceased to function. This temporal dimension is one of the most quietly extraordinary aspects of the Enceladus story. Habitability is not just about having the right ingredients in the right conditions, it is about having them for long enough. Life on Earth took approximately 500 million years to emerge after the planet's surface became stable enough to support liquid water. Some estimates push that timeline shorter, suggesting life may have appeared within a few 100 million years of the formation of the oceans. But even the most optimistic estimates require hundreds of millions of years of sustained habitable conditions. A world that is habitable for only a brief geological episode, a few tens of millions of years before its ocean freezes or its energy source fails, may never cross the threshold from chemistry to biology. The 2025 discovery that Enceladus is in approximate thermal equilibrium, with tidal heat generation matching heat loss through the ice shell, implies that the current state could be stable across billions of years. If the ocean has existed for even a fraction of that time, the conditions for the origin of life have been present far longer than the window that was apparently sufficient on Earth. Time is not the limiting factor. Energy is not the limiting factor. Chemistry is not the limiting factor. Every parameter that scientists can measure or infer points toward an environment that is not merely transiently habitable, but persistently, stubbornly, almost defiantly habitable, maintained by forces that operate independently of sunlight, independently of the moon's own size, and independently of every intuition that says a world this small should be dead. This is the core of what makes Enceladus so unsettling. It is not simply that the moon has geysers. Geysers are spectacular, but they are mechanisms, plumbing. It is not simply that the moon has an ocean. Oceans may turn out to be common in the outer solar system. It is that Enceladus combines active geology, a global ocean, hydrothermal chemistry, all 6 elements of life, complex organic synthesis, and long-term thermal stability in a single package, and that this package is wrapped inside a world so small and so distant that it spent over 2 centuries being ignored. The history of Enceladus in science is a history of underestimation. William Herschel discovered it in 1789 and moved on. The Voyager spacecraft photographed it and flagged an anomaly that nobody followed up on for 20 years. The Cassini mission allocated it a secondary role behind Titan, the glamorous giant with the thick atmosphere and methane lakes. At every stage, Enceladus was treated as a supporting character in someone else's story, a background extra in the grand drama of Saturn system exploration. The background extra turned out to be the lead. There is a lesson in this that extends beyond planetary science. Assumptions are invisible constraints. The assumption that small bodies are dead prevented scientists from looking closely at Enceladus for decades. The assumption that habitable environments require proximity to a star blinded the community to the possibility of tidal-heated ocean worlds. The assumption that geological complexity requires large size made it seem unnecessary to send instruments capable of detecting biosignatures to a moon that barely qualifies as a major satellite. Each assumption was reasonable. Each was supported by the available evidence. And each turned out to be wrong in exactly the way that mattered most. Enceladus now sits alongside Earth, Europa and Mars as one of the 4 most important targets for astrobiology in the solar system. Some researchers argue it should be the top priority, precisely because its plumes offer direct access to subsurface ocean material without the engineering nightmare of drilling through kilometers of ice. Others maintain that Europa's larger ocean and greater total energy budget make it a more compelling target for sustained biological activity. The debate is productive and ongoing. But the fact that a moon 500 kilometers wide is even part of this conversation represents one of the most dramatic reversals in the history of planetary exploration. Consider what the solar system looked like in the year 2000. Mars was the astrobiology target. The search for life beyond Earth was essentially synonymous with the search for evidence of past water on Mars. Europa was a rising contender, thanks to Galileo mission data suggesting a subsurface ocean. Enceladus was not in the conversation. It was a frozen dot orbiting Saturn. It appeared in catalogues. It did not appear in strategy documents. Nobody was proposing missions to it. Nobody was debating its habitability. Nobody was wondering what its chemistry might reveal about the origin of life. The shift happened gradually at first, then all at once. After Cassini's initial plume detection in 2005, a handful of researchers began publishing mission concepts for dedicated Enceladus spacecraft. These early proposals were speculative, underfunded, and largely ignored by the broader community. Mars dominated the astrobiology budget. Europa was the emerging challenger. Enceladus was too new, too small, too far from the institutional momentum that determines which missions get built. But the evidence kept accumulating. Each new Cassini flyby added another line to the case. Salts in 2009, molecular hydrogen in 2017, complex organics in 2018. With every detection, the circle of researchers taking Enceladus seriously expanded. Mission concepts multiplied. The Enceladus Life Finder, the life investigation for Enceladus, the explorer of Enceladus and Titan. Each proposal refined the science case, demonstrating that the plumes could be sampled with existing technology and that the measurements needed to detect biosignatures were achievable within realistic engineering constraints. By the time the 2022 Day-K-Dull survey panel convened to set priorities for the next decade of planetary science, Enceladus had become impossible to ignore. The panel reviewed the accumulated evidence, evaluated competing mission concepts, and made a recommendation that would have been unthinkable 20 years earlier. A flagship mission to one of Saturn's minor icy satellites, a world that most panelists had barely heard of at the start of their careers, was ranked as the second highest priority new mission in the entire planetary science portfolio. Only the Uranus orbiter and probe ranked higher, and that mission addressed a fundamentally different set of science questions. For astrobiology specifically, Enceladus had risen from obscurity to the top of the list. A moon that most textbooks did not bother to diagram had become the mission that a generation of scientists wanted to build. 25 years later, Enceladus has a stronger confirmed habitability portfolio than any world in the solar system except Earth. Not a stronger theoretical case, a stronger observational case. The ingredients have been measured, the energy source has been quantified, the thermal balance has been confirmed, The ocean has been characterized. The organic chemistry has been documented, all from a world that was not even on the radar when the century began. This trajectory from obscurity to prominence contains within it a deeper truth about how the universe works. Significance does not correlate with size. Complexity does not require scale. The most extraordinary environment in the outer solar system is not Jupiter with its crushing radiation belts, or Saturn with its magnificent rings, or Titan with its methane weather cycle. It is a moon so small you could drive across it in a few hours if the surface were paved, a world that reflects so much sunlight it appears as a tiny brilliant point, even through powerful telescopes, a frozen sphere that every textbook and every model said should have died before multicellular life evolved on Earth, and it refused. That refusal is the heart of this story. Enceladus refuses to stay dead. It refuses to conform to the expectations that its size and distance impose. It refuses to behave like a small icy moon should behave. Its ocean does not freeze. Its plumes do not stop. Its chemistry does not stagnate. Its hydrothermal vents do not cool. Its thermal budget does not collapse. Every measurement that should have confirmed a dead world instead revealed an active one. Every instrument that should have detected silence instead recorded a signal. The plumes of Enceladus are that signal. They are columns of ocean water erupting through fractures in the ice shell, rising hundreds of kilometers above the surface and dispersing into Saturn's orbital environment where they form and sustain an entire ring of ice particles encircling the planet. They are visible, they are continuous, they are chemically rich, and they are, in the most literal sense imaginable, this moon's refusal to be silent. The interior is screaming through the only channels available to it. Cracks in the ice, geysers of vapor, grains of salt-laden organic-bearing ice flung into the vacuum of space. The ocean cannot be seen, but it can be heard, if you listen with the right instruments. What Enceladus ultimately represents is the possibility that the solar system is far stranger and far more alive than the tidy models of the 20th century allowed. The old picture was clean. Rocky planets near the sun, gas giants far away, moons as afterthoughts. Life, if it existed elsewhere, would be found on Mars or possibly Europa or nowhere at all. The new picture is messier, richer, and more humbling. Ocean worlds may be scattered throughout the outer solar system, in numbers we have not yet counted. Habitable environments may exist wherever tidal forces can heat the interiors of icy moons, regardless of distance from any star. The ingredients for life may be circulating beneath the surfaces of worlds that look, from the outside, like frozen and featureless spheres of ice. We cannot see those oceans, we cannot visit them yet, but Enceladus is telling us they exist. It is telling us through its plumes, through its chemistry, through its stubborn insistence on remaining geologically and chemically active in defiance of every expectation. If life exists in its ocean, it will be the most consequential discovery in the history of science. If life does not exist despite all the right conditions being present, that absence will itself be a profound result, suggesting that the origin of life requires something beyond favourable chemistry, something we do not yet understand. Either answer changes everything, and the answer is sitting there, dissolved in salt water, waiting inside grains of ice erupting from fractures at the south pole of a moon that nobody thought to look at closely until a spacecraft stumbled onto something that should have been impossible. Enceladus is 500 kilometers wide. It orbits nearly 1 billion miles from the Sun. Its surface temperature would freeze carbon dioxide solid. By every rule of planetary science established before 2005, this world should be an inert ball of ice, drifting silently through the darkness of the outer solar system. Instead, it is expelling evidence of a warm saltwater, chemically rich, hydrothermally active global ocean into the vacuum of space, one geyser at a time. And it has been doing this for longer than complex life has existed on Earth. The icy moon refuses to stay dead, and until we go back and know what its plumes are actually saying, the most important discovery in the history of biology may be hiding inside a world that fits inside a single mid-sized American state, orbiting a planet 1 billion miles away, exhaling its secrets into the silence of space, waiting for someone to listen.